Put your hand on the table in front of you. Go ahead, I'll wait. Feel that? Solid, isn't it? Now here's the thing that ought to keep you up at night. That table, your hand, the wall behind you, all of it, is made almost entirely of nothing. I'm not being poetic. I'm telling you a fact that has been verified in laboratories around the world. The atoms that make up everything you see are more than 99.99% empty space. If you removed all the empty space from every atom in every human being on Earth, you could fit the entire human race into a volume the size of a sugar cube. That's 7 billion people in something you could hold between your fingers. And yet, here we are, unable to walk through walls. Why? The answer involves some of the strangest and most beautiful ideas in all of physics. And by the end of this talk, you will understand why solid things are solid, even though they're made of almost nothing. Now let me tell you what we're going to do. We're going to start from the beginning. We're going to think about what atoms really are. We're going to discover what makes them take up space. And we're going to find out that the reason you can't walk through a wall has almost nothing to do with atoms bumping into each other like little billiard balls. The real reason is far more subtle, far more interesting, and it lies at the very heart of quantum mechanics, a principle that not only explains why you can't walk through walls, but explains why you exist at all. Let's start with something familiar. You know what it feels like to push against a wall. You push, and the wall pushes back. That's Newton, right? Equal and opposite reaction. But what's actually happening when you push on a wall? At the surface of your hand, there are atoms. Carbon, hydrogen, oxygen, nitrogen. At the surface of the wall, there are more atoms. Silicon, oxygen, calcium, whatever the wall is made of. When you push, you're bringing the atoms in your hand close to the atoms in the wall. But how close? What happens when atoms get near each other? Here's where the story starts to get interesting. In the early part of this century, well, now it's not so early anymore, but back around 1909, Ernest Rutherford and his colleagues in Manchester decided to probe the structure of the atom. Now, at the time, the popular model of the atom was something called the plum pudding model. This was J. Thomson's idea. He figured the atom was a kind of blob of positive charge with electrons scattered throughout it, like plums in a pudding. Very English, you see. The idea was that the positive charge was smeared out uniformly through the whole atom, and the electrons just sat there, embedded in this positive goo. Rutherford had a different idea. He wanted to see what was really inside. So he got his students, Geiger and Marsden, to fire alpha particles at a thin sheet of gold foil. Alpha particles are helium nuclei, 2 protons and 2 neutrons stuck together. They're positively charged and they're moving fast. The idea was simple. Shoot these little bullets at the gold atoms and see what happens. Now, if the plum pudding model were correct, what would you expect? You'd expect the alpha particles to sail right through. Maybe they'd get deflected a tiny bit, like a bullet going through a bag of cotton candy. A little wobble, but nothing dramatic. The positive charge is spread out, so the electrical force on the alpha particle is never very strong. And indeed, most of the alpha particles went right through the gold foil. No surprise there. But then something happened that nobody expected. Some of the alpha particles bounced back. Not just deflected a little bit. Bounced back, came right back toward where they started. Rutherford described it this way, and I love this quote. It was as if you fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. Now think about that. You shoot at tissue paper and the cannonball bounces back. That doesn't happen unless there's something very hard, very concentrated inside that tissue paper. Rutherford realized what this meant. The positive charge of the atom isn't spread out, it's all concentrated in a tiny, dense core, a nucleus. Most of the atom is empty space. The nucleus is something like 100,000 times smaller than the atom itself. Let me give you a picture of this. If the atom were the size of a football stadium, the nucleus would be about the size of a marble sitting on the 50-yard line. Everything else is empty seats, empty air, nothing. So here we have an atom that is almost entirely empty. The nucleus sits in the middle, tiny and dense, and somewhere out in that vast empty space are the electrons. They're even smaller than the nucleus. If the nucleus is a marble, the electron is smaller than a speck of dust flying around in the stadium. You see the problem now, don't you? If atoms are mostly empty space, why can't things pass through each other? Why don't your atoms just slip through the spaces between the atoms in the wall? After all, the football stadium has plenty of room. Why can't marbles from one stadium pass through another? Here's where we need to understand what electrons really are and what they're doing out there in the atom. The old picture had electrons orbiting the nucleus like planets around the sun, little balls whizzing around in circles. Very neat, very tidy, and completely wrong. Electrons don't orbit like planets. They don't have definite positions and definite paths. An electron isn't really in any one place. It's spread out. It exists as what we call a probability cloud, or an electron cloud. The cloud tells us where the electron is likely to be found if we measure it. But between measurements, the electron isn't really anywhere in particular. It's everywhere in that cloud, all at once, in some sense. Now, why is the electron spread out like that? Why doesn't it just fall into the nucleus? After all, the electron is negatively charged, the nucleus is positively charged. Opposite charges attract. So why doesn't the electron spiral in and crash? This is where Werner Heisenberg comes in, and his famous uncertainty principle. Heisenberg discovered that there's a fundamental limit to how much you can know about a particle. You can't know both where it is and how fast it's moving with perfect accuracy. The more precisely you pin down its position, the more uncertain its momentum becomes, and vice versa. Now, what happens if you try to confine an electron to a very small space, like the volume of a nucleus? You'd be pinning down its position very tightly. But the uncertainty principle says that if you do that, its momentum becomes very uncertain. That means it could be moving very fast. And if it's moving fast, it has a lot of kinetic energy. Here's the key insight. If you try to squeeze an electron into a smaller and smaller space, you don't save energy. You pay energy. The more confined the electron, the faster it has to move. The faster it moves, the more kinetic energy it has. There's a balance. The electron settles at a distance from the nucleus where the electrical attraction pulling it in is balanced by this quantum mechanical pressure pushing it out. That's why atoms have the size they do. Not too big, not too small. Just right, according to the uncertainty principle. So the electron isn't a little ball orbiting at a distance. It's a cloud that fills the atom. And that cloud, that's what takes up space. When you push on a wall, the electron clouds in your hand are running into the electron clouds in the wall. And this is where the magic happens. You might think, well, electrons are negatively charged. Two electrons repel each other. That's true. The electron clouds in your hand and the electron clouds in the wall do repel each other electrically. That's called electrostatic repulsion. It's the same force that makes your hair stand up when you rub a balloon on it. And yes, that electrical repulsion plays a role. When your atoms get close to the wall's atoms, the electron clouds start to overlap a little bit and they push back, like trying to push together two magnets with the same poles facing each other, north against north. They don't want to come together. But wait, is that the whole story? Just electrical repulsion? It turns out, no. There's something else going on, something deeper, something that requires quantum mechanics to understand. And this is the really beautiful part. Let me introduce you to Wolfgang Pauli, an Austrian physicist, brilliant man, sharp tongue, didn't suffer fools gladly. In 1925, Pauli discovered something profound. He found that electrons have a property called spin. Now, spin in quantum mechanics is a bit strange. It's not like a spinning top. You can't see an electron rotating, but electrons have this internal property that we call spin, and it can point in one of two directions. We call them spin up and spin down. Now, here's the crucial thing. Pauli discovered that no two electrons in the same system can ever be in exactly the same quantum state. If two electrons are in the same place, with the same energy, doing the same thing, one has to be spin up and the other spin down. And once you have two electrons like that, you can't add a third. There's no third option. The state is full. This is called the Pauli exclusion principle. Electrons are what we call fermions, and fermions don't like to share. They're exclusive. If one electron is in a certain state, no other electron can be in that exact same state. Now, why does this matter for walking through walls? Think about what happens when you push your hand against the wall. As the atoms get close together, the electron clouds start to overlap. Now, if electrons could all pile on top of each other, if they could all occupy the same space in the same state, the clouds would just merge together. The atoms would compress. Things could pass through things. But electrons can't do that. The exclusion principle forbids it. As the electron clouds try to occupy the same space, they can't all be in the same quantum state. So what happens? They have to go into different states, higher energy states, and that costs energy. Let me put it this way. If you tried to push two atoms together so that their electron clouds overlap completely, the electrons would have to rearrange themselves into higher energy levels. That takes energy, a lot of energy. The closer you push, the more energy it takes. It's like trying to squeeze marbles into a jar that's already full. You can't just cram more in. Something's got to give. This resistance to compression, this refusal of electrons to occupy the same quantum state, this is what gives matter its solidity. It's sometimes called degeneracy pressure, though that's a bit of a technical term. The point is, it's the Pauli exclusion principle that makes solid things solid. Feynman said it himself. Let me see if I can remember the exact words. He said something like, it is the fact that the electrons cannot all get on top of each other that makes tables and everything else solid. If we could put all the electrons in the same place, matter would condense even more than it does. But we can't. The exclusion principle won't allow it. So there are really two things going on when you push on a wall. First, the electron clouds repel each other electrically. That's real. That matters. But second, and perhaps more importantly, the exclusion principle forbids the electrons from overlapping in the same quantum state. The combination of these two effects is what makes matter impenetrable. Let me give you another way to think about this. Imagine you're at a crowded party, and everyone wants to stand in the same corner of the room. But there's a rule. No two people can occupy exactly the same spot. So what happens? People spread out. They take up space. The room fills up. If you try to push more people in, they push back. Not because they're necessarily bumping into each other physically, but because the rule says they can't all be in the same place. That's roughly what electrons are doing. They spread out, they fill up the available quantum states, and when you try to push more into the same space, they push back. That's why you can't walk through walls. Now wait. I know what some of you are thinking. You've heard about quantum tunneling. Isn't there some quantum mechanical way that particles can pass through barriers? Doesn't that mean, at least in principle, that you could walk through a wall? All right, let's talk about that. Because yes, quantum tunneling is real. It happens all the time for very small particles. Let me explain what it is and then explain why you shouldn't hold your breath waiting to quantum tunnel through your bedroom wall. In classical physics, if a ball doesn't have enough energy to get over a hill, it just bounces back. That's it. No exceptions. If the hill is 10 meters high and the ball only has enough energy to go 5 meters, it's not getting over. But in quantum mechanics, particles aren't just little balls. They're also waves. And waves do something interesting when they encounter a barrier. They don't just stop, they decay into the barrier. The wave amplitude gets smaller and smaller as it goes through the barrier. And if the barrier is thin enough, a little bit of the wave makes it out the other side. What does that mean? It means there's some probability, some chance, that the particle will be found on the other side of the barrier, even though it didn't have enough energy to go over it classically. The particle tunnels through. It doesn't go over, it doesn't go around, it goes through, as if it teleported. This is not science fiction. This is measured in laboratories. Electrons tunnel through barriers all the time. The scanning tunneling microscope, which can image individual atoms, works precisely because electrons tunnel between a sharp tip and a surface. Nuclear fusion in the sun happens because protons tunnel through the electrical barrier that normally keeps them apart. Alpha particles tunnel out of unstable nuclei, which is how radioactive decay works. So tunneling is real. The question is, could you tunnel through a wall? Here's the thing. The probability of tunneling depends on several factors: the mass of the particle, the width of the barrier, and the height of the barrier. The more massive the particle, the less likely it is to tunnel. The wider the barrier, the less likely. The higher the barrier, the less likely. Now, an electron is tiny. Its mass is about 9 times 10 to the minus 31 kilograms. That's practically nothing. And even for an electron, tunneling through anything more than a few atomic widths, a few angstroms, a few tenths of a nanometer, becomes extremely unlikely. A wall is not a few angstroms thick. A wall is centimeters thick, tens of billions of atomic widths. The probability of a single electron tunneling through a wall is so small that the number is essentially zero for any practical purpose. But you're not a single electron. You're made of about 7 times 10 to the 27 atoms. That's 7 billion atoms. Each of those atoms has electrons, protons, and neutrons. For you to tunnel through a wall, every single one of those particles would have to tunnel at the same time, in the same direction, and come back together on the other side. The probability of that is so small that there's no number in everyday language to describe it. We're talking about probabilities like 10 to the minus 10 to the 30. That's a number so small that if you waited the entire age of the universe, multiplied by another age of the universe, multiplied by another, over and over, 1 trillion times, you still wouldn't expect it to happen. Not once, not ever. So yes, quantum mechanics says there's technically a non-zero probability that you could quantum tunnel through a wall, but practically speaking, it will never happen. Not to you, not to me, not to anyone. The laws of physics don't actually prevent it, but the numbers are so against you that it's not worth considering. Here's another way to think about it. The probability of winning the lottery is tiny, but compared to the probability of quantum tunneling through a wall, winning the lottery is a certainty. You would have a better chance of winning the lottery every day for the rest of your life than tunneling through a wall once. So put that idea out of your mind. You are not going to walk through walls. The electrons won't let you. Let me pause here and make sure we've got the main idea. I want to explain this as simply as I can, as if I were talking to a bright 12-year-old. Here's the deal. Everything is made of atoms. Atoms are almost entirely empty space. But the electrons in atoms don't let other electrons occupy the same space. This isn't just electrical repulsion, though that's part of it. It's a fundamental rule of quantum mechanics. Electrons are fermions, and fermions are exclusive. 2 fermions cannot be in the same quantum state. When you try to push 2 atoms together, the electrons resist because they'd have to pile into the same states, and they can't. That resistance is what we feel as solidity. That's why walls are solid, even though they're made mostly of nothing. Now let me tell you about a common misconception. Some people think that the reason we can't walk through walls is just because atoms are hard. They imagine atoms as little solid spheres like tiny marbles. And when you push 2 marbles together, they can't occupy the same space. Simple. But that picture is wrong. Atoms aren't solid spheres. Atoms are clouds of probability. The nucleus is tiny. The electrons are spread out in a fuzzy cloud. If you try to push 2 atoms together in classical physics, with the electrons as little particles orbiting like planets, there's no obvious reason why the atoms couldn't interpenetrate. Why couldn't one set of electrons just orbit around the other nucleus while the atoms overlapped? In classical physics, that would be weird, but not impossible. It's only when you bring in quantum mechanics, specifically the exclusion principle, that you understand why matter is impenetrable. The electrons can't share the same states. They have to spread out. They resist compression. That's the secret. Another misconception. People sometimes say that we never really touch anything. That when you put your hand on a table, the atoms never actually make contact. There's always a tiny gap, and what you feel is just the electrical repulsion between electron clouds. This is one of those half-truths that gets physicists into trouble at parties. Is it true? Sort of, but it's misleading. Yes, in some sense, the nuclei of your atoms and the nuclei of the table's atoms are never in contact. They stay apart. The electron clouds push back before the nuclei can meet. But the electron clouds themselves are overlapping. They're interacting. They're exchanging forces. If that's not touching, then what is? The problem is that touch is a macroscopic concept. We know what it means for your finger to touch a table. We feel it. But when you try to take that concept down to the atomic level, it gets fuzzy. Literally fuzzy. Because electrons are fuzzy. At the quantum level, the concept of contact just doesn't translate neatly. So don't get too hung up on whether atoms really touch. What matters is that atoms interact. They push back. They resist interpenetration. And that's what we experience as solid matter. Now, I want to do a little thought experiment with you. This is important for really understanding what's going on. Imagine you could shrink yourself down to the size of an atom. You're standing on an atom in your hand, looking at an atom in the wall. What would you see? First of all, you wouldn't see much of anything. Electrons don't have a color. They're not reflecting light in any normal sense. But let's pretend you have some magical atom-sized flashlight. You'd see the nucleus of your atom, tiny and bright, like a sun. And far away, relatively speaking, you'd see the electron cloud, a kind of misty sphere surrounding the nucleus. And then, across a vast distance, you'd see the wall atom, its own nucleus, its own electron cloud. As your atom approaches the wall atom, you'd start to notice something. The electron clouds are overlapping. And as they overlap, they're not merging smoothly. They're pushing back. There's a resistance. It's hard to get closer. The closer you try to get, the harder it pushes. You might be tempted to try to slip between the electrons. After all, the cloud is mostly empty, right? But here's the thing. The cloud isn't a collection of dots that you could navigate between. The cloud is the electron. The electron is the cloud. There's no path through. The whole region is occupied by the electron in a quantum mechanical sense. And because of the exclusion principle, the electrons in your atom and the electrons in the wall atom cannot share that space in the same quantum states. They push back. That's the barrier. Not a physical wall within the atom, but a quantum mechanical barrier of occupancy. So there you have it. At the atomic level, walking through a wall would mean forcing electrons to share quantum states that they cannot share. The universe doesn't allow it. The math doesn't permit it. The electrons refuse. Let me talk about something else now. What if there were no exclusion principle? What if electrons were bosons instead of fermions? Bosons are the other kind of particle. Photons are bosons. So are some atoms, like helium-4, at very low temperatures. Bosons don't have the exclusion principle. They can all pile into the same quantum state. In fact, they like to. They're gregarious. Give them a chance, and they'll all crowd into the same place. If electrons were bosons, everything would be different. All the electrons in an atom would fall into the lowest energy state, right next to the nucleus. There would be no electron clouds spreading out. Atoms would be much, much smaller. And when you brought two atoms together, their electrons wouldn't resist sharing states. They'd be happy to pile on top of each other. Matter wouldn't be rigid. It might not even be solid. Everything would collapse into dense blobs. Chemistry as we know it wouldn't exist, because chemistry depends on the arrangement of electrons in shells and orbitals, and that arrangement only exists because of the exclusion principle. In other words, if the exclusion principle weren't true, you wouldn't exist. Neither would I. Neither would anything we recognize as matter. The exclusion principle is one of the fundamental rules that makes the universe habitable. Now, let me tell you something truly remarkable. The stability of matter on a large scale, the fact that you can build structures out of atoms and they hold together, this was actually proved mathematically. In 1967, Freeman Dyson and Andrew Leonard showed rigorously that ordinary matter is stable because of the Pauli exclusion principle. Without it, the attractive forces between electrons and nuclei would cause everything to collapse. The exclusion principle provides a kind of pressure that holds things up. Later, in 1975, Elliott Lieb and Walter Thuring found a simpler proof. They showed that there's a lower limit to the energy of a collection of electrons, and that limit depends on the exclusion principle. It's the quantum mechanical version of why you can't squeeze matter down to nothing. So when you sit on a chair, and the chair holds you up, thank the exclusion principle. When a building stands without collapsing, thank the exclusion principle. When the Earth holds together as a solid planet, the exclusion principle is doing its work. There's actually a place in the universe where even the exclusion principle is pushed to its limits. That's in a white dwarf star. A white dwarf is what's left when a star like our Sun runs out of fuel. The outer layers blow off and the core is left behind. It's incredibly dense, about the mass of the Sun squeezed into something the size of the Earth. A teaspoon of white dwarf material would weigh tons. What holds up a white dwarf against its own gravity? Not nuclear fusion. That's done. Not thermal pressure. The star is cooling down. What holds it up is electron degeneracy pressure. The electrons are squeezed together as tightly as the exclusion principle allows. They're occupying every available quantum state, and they refuse to be compressed any further. That's the exclusion principle in action on a cosmic scale. The same principle that keeps your hand from going through a table is holding up a dead star against the crushing force of gravity. And if the star is too massive, if there's too much gravity, then even electron degeneracy pressure isn't enough. The electrons get pushed so hard that they merge with protons to form neutrons. You get a neutron star, where neutron degeneracy pressure takes over. Neutrons are also fermions, so they also obey the exclusion principle. A neutron star is held up by neutrons refusing to share quantum states. And if even that's not enough, then you get a black hole. Nothing can hold it up. The exclusion principle loses. Gravity wins. Everything collapses into a singularity. But for ordinary matter, on ordinary scales, the exclusion principle is more than enough. It makes atoms take up space. It makes matter solid. It makes walls impenetrable. Let me bring this back to the beginning. You put your hand on the table. You feel resistance. Why? Because the atoms in your hand have electron clouds. The atoms in the table have electron clouds. Those clouds are governed by the Pauli exclusion principle. When the clouds approach each other, when they try to overlap, the electrons can't share the same quantum states. They resist. They push back. What you feel is the hardness of the table, the solidity of the wall, is the exclusion principle at work. It's quantum mechanics manifesting at the macroscopic scale. It's the reason things are solid even though they're made of almost nothing. And it's deeply, beautifully strange because there's no force, exactly, that's pushing the atoms apart in the traditional sense. It's not like magnetism or gravity. It's a statistical constraint, a rule about what states electrons can occupy. And yet it's strong enough to keep buildings standing, to keep planets intact, to keep you from falling through the floor. That, to me, is one of the great miracles of physics. That such an abstract mathematical principle, discovered by a young Austrian physicist thinking about electron configurations in atoms, has such concrete, visible, tangible consequences. When you lean on a wall, you're not really leaning on bricks and mortar. You're leaning on a quantum mechanical principle. The wall is solid because electrons are fermions, and fermions don't share. So the next time someone asks you why you can't walk through walls, you can tell them. It's not because atoms are solid balls. It's not just because electrons repel. It's because of the Pauli exclusion principle. It's because electrons cannot occupy the same quantum state. It's because of quantum mechanics. And in a deep sense, the solidity of the world around you, everything you can touch and feel and push against, all of it is a consequence of that one simple rule. No two fermions in the same state. That's it. That's the secret to why the world is solid. Now, there's one more thing I want to leave you with. A big picture thought about what this all means. We live in a universe where the rules of quantum mechanics are strange. Particles are waves. Waves are particles. You can't know position and momentum at the same time. Electrons don't have definite locations until you measure them. It all sounds like fantasy. And yet, these strange rules produce the familiar world. The chair you're sitting on, the ground beneath your feet, the walls that keep the wind out. All of it comes from quantum mechanics. The solidity, the structure, the chemistry, all of it. There's something wonderful about that. The quantum world seems crazy, unpredictable, probabilistic, but out of that chaos comes order. Out of fuzzy probability clouds come hard tables. Out of uncertainty comes certainty at the macroscopic scale. The exclusion principle is part of that magic. It takes the randomness of electrons and imposes structure. It makes atoms have shells. It makes the periodic table work. It makes chemistry possible. And it makes matter solid. So the next time you walk into a wall, and I hope that doesn't happen too often, but if it does, take a moment to appreciate the physics. That wall is solid because of one of the most elegant and strange rules in all of nature. The Pauli exclusion principle, the rule that says electrons won't share, and that's why you can't walk through walls. It's not because the universe is trying to stop you. It's because the universe is put together in a certain way with certain rules, and those rules have consequences. Beautiful, strange, wonderful consequences. Thank you for letting me share this with you. Now I'm curious. What everyday experience makes you wonder, as I often do, what strange physics might be going on behind the scenes? Write down your thoughts and share them. The best conversations start with the best questions.